a peer queries a tracker for a list of other peers. So what happens is, an important thing to note is that because we wanted our device to be unobtrusive, not only unobtrusive in terms of not degrading client and user performance, but also we didn't want to require any changes to the protocol. So in addition to emulating a local ISP local tracker, our device also needs to identify messages on the wire, extract metadata from those messages, and respond directly to peers. So we'll briefly go through the operation of our device. So let's go back to our scenario. Now the way peer works is I consider this scenario where we have two access ISPs. We have Bob again, Bob is back, and he contacts a tracker. The tracker now returns its random list of peers. So now Bob is equally likely to connect to any one of those peers. Now let's install peer on this access ISP router. And so we install peer, and this is how the scenario changes. When Bob tries to connect to the tracker, peer detects that message, directly responds to Bob, and informs Bob of only ISP local peers. Now the way it works currently is that the policy that we use, it's a first response policy. So we only detect the first query to the tracker and respond directly to that query. In fact, Bob also connects to the tracker periodically later for more peers or to update statistics, such as only the percentage of the file that he has downloaded. So let's briefly look under the hood and see how peer is designed. So basically, peer consists of 4 components. So imagine incoming packets on the wire. There's a filter component that detects control messages, queries to the tracker. There's a parser component that essentially extracts the metadata from the query. And there's an oracle component that makes a decision whether to reply or not and implements our first response policy. And there's also a proxy cache, which stores a list of, so the oracle decides whether it should respond or not to that query and makes that decision. Assuming that it decides not to, it forwards the packet onto the application tracker, the message onto the application tracker. The proxy cache responds to the message. Now, you might want to ask, why do we decouple the proxy cache and the oracle when the functionality could essentially be one component? But what you'll notice is that we wanted a situation where we wanted to maintain high performance, and if we had a situation where we would put the proxy cache data structure, which is pretty expensive in terms of cycles and memory accesses to generate a application level packet. So we wanted to decouple that from the oracle in the sense that we could keep the system, we could maintain high performance and keep the system running smoothly. So that's one of the reasons why we chose this design where we decoupled the oracle and the proxy cache. So the next, and this is when the proxy cache sends a response to the application tracker. So then we implemented this device on programmable routers in the Open Network Lab. The Open Network Lab, if you're not familiar with it, is just a bunch of programmable routers and end host. So we chose the Open Network Lab because we could actually experimentally evaluate our device as opposed to just building something and saying that it works. So we built this and we used programmable routers on ONL and we evaluated our device. Obviously the goal at that point is to compare transit traffic with peer and without peer. So a component under study would be a transit link, and we came up with metrics that would serve the purpose of upstream, downstream transit link utilization. When we say utilization, we mean if there's a 1 megabyte file that is transmitted on the link, then if 1 megabyte of traffic travels that link, then the utilization is effectively 1, so you basically divide by the file size, so that's what we mean by utilization. And also we wanted to consider the impact on end user performance, so another metric that we included is download time. Now we only consider the flash crawl workload, which is a workload where a popular file is just made available and everybody basically connects trying to download that file quickly. That's one of the most taxing workloads on the transit link and on the system as a whole. The other workloads that we could have considered, we initially started with flash crawl workload. Okay, so one of the things we needed to do is identify what parameters affect our workload and the system. We identified these parameters and then we identified what factors are we going to study. So these are the factors that we decided to study. The choice of tracker, either peer or not peer, and number of leechers, factor we call a degree of locality, which I'll explain a little further. Peer behavior is an interesting factor because what happens is that typically you would expect as a peer is done, completed, becomes a seeder, has finished downloading the file, he has a choice of either staying around and being a nice guy and sharing with the other peers, or just disconnecting immediately and being a bad boy. So we also consider file size, and there's something called, which we call the initial location of the seeder, where we consider a scenario where the seeder is local to the ISP or external to the ISP, the initial location. So now we have all these factors and we wanted to maximize our use of time, so we decided to design a fractional factorial experimental design where what we did is we only considered two levels of each factor to determine what variability that they explain in terms of our two metrics. So these are the two levels of each factor that we considered. I show you for number of leeches 20 to 200, degree of locality, low in terms of low number of ISP local pairs, and high. And then the two types of behavior, file sizes, and initial seeder location. So we consider those two levels. We did this design. So if we only consider those two levels, we'd have to do 64 experiments. So we need to break that down into 16. That's where the design came in of our experiment. So we only had to do 16 experiments. And then we could see what factors account for what amount of variability in terms of our link utilization and our download time. So what we noticed is that for download time, 95% of the variability is due to file size, which is pretty cool because it shows that the presence of peer doesn't necessarily have a significant impact on download time, which is what we want. So we also consider what upstream and downstream, upstream would be and downstream utilization of the transit link, and we noticed that again, number of leeches has the most significant factor in terms of variability in those two metrics. However, if we consider them individually, we can see that for upstream utilization, the tracker and the degree of locality are the next two important factors, so therefore that requires further study. Also for downstream utilization, the factors are different. Actually, it's what we notice, it's that the initial location of the seed is what's important in this case. And again, the number of leeches, as we said. So now that we know what factors account for most of the variability in our metrics, we proceed a little further and do some experiments based on those factors. So what did our experiments show? So basically, what this shows for the top one is we looked at the factors that account for most of the variability in upstream link utilization, and the top graphs consider only the degree of locality and obviously the choice of tracker. So what you notice is for 20 leeches scenario, it's 10%, 50%, and 100% locality. So 10% in that case, locality would mean that there are two.
Can you read the labels? I can't tell what those charts are showing.
The first chart shows the degree of locality and upstream link utilization. Each label on the three groups categories: 10%, 50%, and 100%. So what the 10% category represents is a scenario where, so the first one is 20 leeches, the second one is 100 leeches, the third one is 200 leeches. So each one has 10%, 50%, and 100%. 10% represents a scenario for 20 leeches, there will be 2 local ISP pairs and 18 external pairs. So we looked at that situation, and 50% would mean 10 to 10, so forth. So in that situation, we noticed that peer does do a lot better in terms, because it's a lower is better metric, because lower the link utilization.
This is showing the upstream link utilization. Is that your y-axis here?
Yes, yes. The y-axis is upstream link utilization. So it's a lower is better metric. So you can see peer is lower, not significantly, there's not a huge gap in terms, but you can see it's better. But remember, we only did a first response policy, so there are other more aggressive tactics that we could possibly use. So the red line actually shows a perfect scenario where, because what we did for the first experiment is that we limited the impact of other factors. So in the first experiment, there are 2 seeders. There's a local seeder and there's an external seeder as well. So in this case, the ideal locality would be, the ideal link utilization would be 0. Because if you think about it, there's actually a local seed present on the ISP's network. So therefore, the best you can possibly do is no transit traffic at all. In the second scenario, we looked at the factors that we saw accounting for most of the variability in downstream link utilization, which was the initial location of the seed. So we varied the location of the seed. So in this case, link utilization is on the y-axis, and there's